Hi, I'm Talia Gillis from Columbia University, and I'll be talking about joint work with Jann Spiess and Bryce McLaughlin from Stanford University, in which we consider how properties of machine learning predictions affect the resulting human decisions. As there is increased use of algorithms in decision-making in critical domains, capturing the benefits of increased accuracy while making sure decisions are fair and non-discriminatory is a key concern. Consider the domain of consumer finance, where there have been several examples of claims of discriminatory algorithms. One salient example was with Apple Card. Apple Card, issued by Goldman Sachs, uses big data to set highly personalized credit terms. This card was the center of attention in August 2019, when a husband received 20 times the credit limit of his wife, despite them having similar assets and the wife's higher credit score. This prompted an investigation by the New York Department of Financial Services, which ultimately concluded that the algorithm was not discriminatory. What is central is that the claim and investigation focused on this presumably black box algorithm that was determining credit card terms and whether it was fair in that it provided different terms for individuals who had similar credit scores but were of different genders. But when we think of fairness in this context, we need to pay attention to how an algorithmic decision is applied. One way an algorithmic prediction is applied is by directly translating the prediction into a decision. So suppose Apple Card had trained a model to predict borrower creditworthiness so that when there is a new applicant, the individual features are translated into a decision with respect to that borrower's credit limit. We call this automation. And a significant part of the algorithmic fairness literature and much of the legal and policy literature focuses explicitly or implicitly on analyzing a prediction when an algorithm implements a decision directly. But in many of the critical applications, we see a very different model in which a prediction is given to a human decision maker that has decision-making authority. For example, Apple Card's algorithmic recommendation, like a prediction of creditworthiness, could be provided to an Apple Card employee who would then decide the credit limit. We call this assistance. And this model of decision-making, in which the algorithm acts as a decision aid to a human decision maker, is prevalent in many critical decision-making domains, such as employment and bail decisions, and is often mandated by legal rules. So in the paper, we compare some of the results of the algorithmic fairness literature to their counterparts in the decision system where a human decision maker takes the prediction as an input. So I'll start with what we see as our contribution and key insights. What we do is we compare two very simple algorithms, essentially conditional averages, which vary based on whether they use a protected characteristic focusing on gender to enforce some prediction. And we have two main metrics of interest. For our fairness metric, we look at the expected difference in how the decision system or decision maker is going to be implementing the decision across gender, holding all other features consistent. So think of X as a large covariate set. For accuracy, we look at the expected mean square error of the prediction. Now, what we do essentially is we compare these two metrics when we include and exclude the protected characteristics in the two decision systems. Under automation, where the decision itself is the conditional average, and under assistance, where the decision is determined by a human who has some prior beliefs, seeking to maximize accuracy after seeing the conditional average. So in our setup, we have the same prediction algorithm, but we have a human that decides what to do with the prediction. Our key results are that with automation, using gender to form a conditional average increases disparity. And this is simply because it allows for the direct differentiation based on gender. This is the classic trade-off between accuracy and fairness. But under assistance, the causal effect of including gender completely depends on who is getting the signal. And to demonstrate this, we focus on a context of a human decision maker with an inaccurate statistical bias. In such a case, the use of gender in the conditional average can decrease disparity, creating an alignment between risk minimization and fairness. So to clarify, we're not arguing that including protected characteristics always reduces disparities. Rather, it can, because decision outcomes depend on who receives the signal. Our analysis builds on the large literature of algorithmic fairness, much of which focuses on a decision structure of automation. But we highlight that how properties of the underlying prediction algorithm affect the decision doesn't directly translate into the context of assistance. We therefore focus on the centrality of the implementation to the question of algorithmic design. We also provide one more reason to be skeptical about a blanket approach to excluding protected characteristics, which is quite prevalent in legal and policy writings. So in our model, individuals have X characteristics, we think of these as observables, and a protected characteristic, gender. And we want a decision that when measured against the true label minimizes the mean square error, that's our loss function. So think, for example, if we're trying to predict whether a borrower will default on the loan and we have information on their income, their wealth, credit score, and gender, and we're looking to minimize the mean square error between the predicted default and whether they truly default. Imagine we also have access to some training data. So this could be kind of past borrowers who receive loans. And we have two prediction functions. We have a conditional average without gender and a conditional average with gender. We also have a Bayesian decision maker who has prior beliefs and takes decisions to minimize expected loss given the conditional average. So what is key is that there's no misalignment in incentives because the human decision maker also seeks to minimize loss. But we also make a special condition. We assume that the prior of this Bayesian decision maker is bias, in that the marginal impact of gender is not zero. So the decision maker's prior is biased in that they believe that if they observe the general average across men and women for type X, they still believe there would be some disparity. So I'll now use a stylized example just to build up intuition, but our results hold more generally. So I want you to assume that there's only one type of X characteristics, so that all that distinguishes people is their gender, and assume that people are roughly half female, half male. Y is our default probability, which is distributed normally with a mean that varies by gender, but variance that does not vary by gender, and the means are distinct. The assumptions we make about a decision maker is that they know that this is a normal distribution, but they don't know the mean, and they have some prior belief on the mean, and they make a decision to minimize their expected loss. So what happens under automation? Remember, we're holding all other covariates fixed. When we don't use gender in the conditional average, we take a singular decision. But when we bring this extra covariate in, gender, we are allowing the decision to change on the basis of gender. So information provides the differentiation essentially between men and women. But now let's assume we're in the world of assistance. The human decision maker now receives an average and now makes a prediction. So the decision maker is given the conditional average, they combine their prior with the normal signal to create a posterior expectation. What happens when the conditional average does not include gender? So the decision maker believes the distribution of default probability are here for men and women, and the lines are essentially the mean for men and women. So without any additional signal, these lines would kind of be the prediction for men and women. And then in the black, we have the average for men and women. Now let's assume this human decision maker has access to a conditional average without gender. So the average of default probabilities for the full population. And it turns out that it's lower than the prior average. This leads the decision to a decision that's shifted to the left. So the gap in the means remains the same, but it simply shifts in the direction of the average of the signal received. Intuitively, decision maker only updates with respect to the combined average, but not the differences in average. Now, what happens when you provide a signal that includes gender with gender? Again, you have the decision maker's beliefs for men and women, but now you receive separate signals for men and women. This essentially leads to a shift in the posterior for men and women. They both shift in the respective direction of the conditional average. So in this example, I'm assuming that the prior on the differences in means is larger than the true differences. This is essentially the inaccurate statistical bias. So by having separate means, the decision for men and women become essentially closer to one another. It's as if we're countering the bias through presenting information that includes gender. Now, this result applies more generally. When the decision maker has a bias that's greater than the true difference, then under automation, there are higher disparities when we include gender, but also higher precision when we include gender. This is the classic trade-off between disparity and precision. But under assistance, when the algorithm has access to gender, we can lower disparities and also have higher precision, so that providing a conditional average with gender dominates in both disparity and precision. Now, the purpose of this paper is not to say that we should always include protected characteristics in an algorithm. Rather, when we consider the impact of an algorithm, we have to be sensitive to how it's going to be implemented. Focusing on a particular context, we show that the inclusion of a biased human decision maker can revert common relationships between the structure of the algorithm and the qualities of the resulting decisions. While our concrete results rely on specific assumptions, our broader point is that study of critical properties of complex decision systems should go beyond focusing on the underlying algorithmic predictions in isolation. Thank you.